Okay, so what is an inner product? The inner product, we define the inner product of two vectors. All right, suppose I have a vector u and another vector v. Okay, all right, the inner product of these two vectors, we often write this like this. The inner product of these two vectors is a rule that takes input these two vectors and outputs a scalar. All right, well, simple enough. Basically, an inner product is like a machine. In this machine you will give the two vectors as input. Okay, one vector u, one vector v, and the machine outputs a number. Okay, actually you have been using inner products well, for a very long time. The dot product in vector algebra that we have been using for, well, you have been using since the time of your HSC studies. All right, that is actually an inner product. Okay, so suppose I have a vector, well, I have a vector r1 that is like this: a1i plus b1j plus c1k, and I have a another vector r2 that is a2i plus b2j plus c2k. Okay, so, well, if we form the dot product of these two vectors, the result will be, you know, a1 a2 plus b1 b2 plus c1 c2. So you see that this is actually a number. All right, this is a number. So the operation of dot product, it took as input two vectors, one vector r1 and another vector r2, and it output this number. Okay, so a dot product is an inner product. Okay, a dot product is an example of an inner product. All right, so like the dot product, we can have other rules of inner products, but, well, this is the most common rule. Okay, this is actually called the Euclidean inner product. Okay, all right. So this rule of dot product or inner product was made for real vector spaces, since in real life, in the geometry vector space that we use, all of these numbers a1 a2 b1 b2 c1 c2 are all real numbers. All right, so for complex vector spaces, since in quantum mechanics we will be working with complex vector spaces, we need to generalize this rule. Okay, so the generalization that we will use for complex vector spaces is this. Suppose we have a vector. Okay, since we will be explicitly working with column matrices, we suppose we have a vector u. All right, we have a1 a2 dot dot dot. Suppose we have an n-dimensional vector space. an, and we have another vector v that is b1 b2 dot 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 bn. All right, so the inner product of u and v, all right, it will be, mind that we are working now explicitly with complex vector spaces. Okay, I will write that so that we can keep track of it. Complex vector space. All right, so all these numbers are complex numbers. Okay, these a1, a2, b1, b2, all of these numbers are complex numbers. So for complex vector spaces, our definition of inner product is going to be, if we want to form the inner product of two vectors u and v, our inner product is going to be a1 conjugate times b1 plus a2 conjugate times b2 plus dot 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 an conjugate times bn. All right, so if we compare with our original definition of the dot product or inner product, for moving to complex numbers, what we have to do is we have to take the complex conjugate of the first number in our inner product. All right, for real vector spaces, well, the complex conjugate of a real number is a real number, so it's actually invariant to whether we take the complex conjugate of one or not. But for complex vector spaces, for the first vector that we input to the inner product function, we have to take the complex conjugate of the components. And let me give a slight recap of what is a complex conjugate is. Suppose I have a complex number a1 which is of the form x1 plus I y1. Okay, so here x1 and y1 are both real numbers. All right, so the complex conjugate of a1 will be x1 minus I y1. All right, so the imaginary part, if it was plus I, it will be replaced by minus I. Okay, the imaginary part, there will be a change in sign. This is the definition of our inner product for a complex vector space. So we can actually write this line a little more compactly. All right, we can write this line a little more compactly. We can write this as a matrix multiplication. How? See, if I define a row vector like this, a1 conjugate a2 conjugate dot 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 an conjugate. All right, this is a row vector times a column vector b1 b2 dot dot bn. All right, if we multiply this row vector by this column vector, all right, we will actually get this number. Okay, we will actually get this number. How? We know that when we matrix multiply, we take one row and one column and we multiply all the elements element wise, and then add our results. So well, there is only one row here and there is only one column here, so if we multiply we will just get one number. So this vector, this column vector, is actually equal to the vector that we had before. All right, this is actually equal to the vector v. What is this one? Well, it is actually, this is not u, not exactly u, this is different from u. You see that u was a column vector and this one is a row vector, and in u we had a1 a2 dot 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 an. In this row vector we have all the complex conjugates of a1 a2 dot 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 an. So do you know of a mathematical operation that can convert a row vector to a column vector or a column vector to a row vector? Okay, we know of such an operation in matrices, that is the transpose of a matrix. All right, the transpose. So if we have a matrix and if we take the transpose of that matrix, as you might remember, then all the columns of the matrix are converted to rows, and the rows are converted to columns. All right. So if we take the transpose of the matrix U, okay, if we take the transpose of the matrix U, we write transpose like this, T, then the matrix we will get is A1 A2 dot 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 AN. Okay, well, this is not quite the same as this one. What difference do we have? Well, in this one we have complex conjugates, and here we don't have any complex conjugates. So to make this vector, we need to do complex conjugate of the transpose matrix. All right, we have to do complex conjugate over the transpose matrix. So then we will get A1 conjugate, A2 conjugate, dot dot dot, AN conjugate. All right, so using this notation, we can write our inner product like this. We can write our inner product like the row vector, the row matrix, the row vector will be U transpose conjugate times V. All right. Okay. So in complex vector spaces, this operation comes many times. All right. We have to do this operation many times. In fact, we may often see that whenever we do a transpose, we will have to take a complex conjugate with it. So to simplify our notation, a symbol was introduced for this operation, this transpose plus complex conjugate. We call this the dagger operation. Okay, so we will write this as U dagger. This is like a small knife or something. U dagger V. Okay, so what does dagger represent? U dagger represents the operation U transpose conjugate. All right, we will take the transpose of a matrix, and then we will take the complex conjugate of the transpose matrix. That is the dagger operation. So our definition of inner product for complex vector spaces is, we have U V equals U dagger V. Okay. All right. Well, that's about it. That's about all the basic things about vector spaces that we need to study the properties of quantum mechanics. Okay, thank you.